Hello and welcome. This is the pre-lecture video for Chapter 11. Depending on how this video goes, I think we'll just have one video for the entire chapter instead of separating it into two separate parts. So let's begin with intermolecular forces. So intermolecular forces are what we describe the interactions between adjacent molecules within a molecular compound when it forms, say, a liquid or a solid structure. So if we have two adjacent molecules in, say, HCl liquid, then the intermolecular force of attraction would be what it is that's bringing those molecules together. Now, a molecule like HCl we know is polar from Chapter 8. So we have a diatomic molecule that's polar. So we have this partial positive, partial negative, partial negative, partial positive on our molecules, uniting them together on this minus on plus. And it's just not very strong. If we think back to something like sodium chloride, we get the plus and the minus, the plus and the minus. The sodium ions and adjacent ions are really as far away as they are from each other in any two NaCl units, meaning that in a structure of like sodium chloride, that you can't really find one molecule of sodium chloride that's somehow further or closer together and then further apart from the next adjacent ion. That's not the way it works. Our plus and minus ions bump right into each other and form a lattice that's very regular in its repeating pattern. Now, HCl can form a lattice. It's just not going to have the H and the Cl in adjacent molecules be closer together than in a single molecule. So if you look at your bond length here compared to your length separating your molecules, notice that the bond length separating our molecules is much bigger. And so that's a consequence of the intermolecular bonds being weaker than the covalent bonds. So we get a relatively stronger covalent bond between one H and one Cl, and a weaker attraction between two HCl molecules. Now, this is a good reason why the boiling point of something like HCl is well below room temperature, whereas the melting point and boiling point of something like an ionic compound of NaCl is much higher than room temperature. So many physical properties like boiling point, melting point, viscosity, surface tension, capillary action, we'll define some of these as we go throughout this chapter, but all of these properties have a fundamental connection to the strengths of intermolecular attraction. So the states of matter, whether a substance exists at room temperature as a gas or a liquid or a solid, has a lot to do with the strengths of intermolecular attraction. So we know I2 is a solid at room temperature, so we're looking at 25 degrees C, I2 is a solid, bromine's a liquid, chlorine's a gas, F2 is a gas. So we can very easily just reason out that the forces that unite iodine molecules must be stronger than the forces that unite bromine molecules, which those forces in bromine are still stronger than they are in Cl2. So temperature is a measure of kinetic energy. So at the same temperature, all of these samples would have the same average kinetic energy. And that average kinetic energy in the case of chlorine is strong enough to overcome its intermolecular forces, hence the intermolecular forces must have been weaker in Cl2, and therefore the forces must be stronger in I2, since at room temperature there's not enough kinetic energy in the sample to allow the I2 molecules to be separated from each other. Okay, so some properties of gases, liquids, and solids. Some of these are very, very basic, like we know gases expand to fill their container. They assume the volume and the shape of their container. They're compressible, flow readily. Gases can diffuse rapidly. Liquids assume the shape of the container, but does not expand to fill the container. Liquids are generally incompressible. So you can compress a liquid. Usually, most liquids would form a solid if you compress them. They certainly flow readily, and they diffuse. Liquids diffuse relatively slowly through each other, where gases will diffuse much more quickly. The solids retain their own shape and volume, of course. They do not expand to fill a container. They are virtually incompressible. Like usually a solid you can't compress further. You would just take a solid and keep it a solid. Water is one interesting exception in that liquid water, if you compress it, it actually won't form a solid. And if you compress solid ice, you can actually form liquid water. So water is a little strange. That's going to be a consequence of the density of ice being less than the density of liquid water. The property that ice floats on water is a good reason why it has a difference in its compressibility. But, of course, solids don't flow, and then diffusion of solids is very, very slow. So the relative strengths of attraction by different types of bonding types. Let's take a look at these. So we have ionic bonds have relatively high melting points. They have relatively high boiling points. They have strong ionic interactions that our molecular compounds just don't have. So things like HF or HCl don't have the full plus-minus attraction like ionic bonds have. So things like HCl, HF end up having lower melting points. Notice these melting points are in the units of Kelvin. So 273 or 298 Kelvin's room temperature. So these are still below room temperature. And the boiling points are as well. Okay, and so if we look at the bonding in HCl and HF, it's weaker than the bonding in the ionic LAF. Well, what about metallic bonds? Metallic elements usually have relatively high melting points and boiling points. Some can have low enough melting points to be liquids, like mercury and almost cesium. And also, we have high melting points in the case of covalent network compounds. We might talk a bit more about the bonding nature of something like carbon in Chapter 12. We discussed it maybe briefly earlier in, I believe, Chapter 2. At some point, I think I showed a slide of carbon, graphite versus diamond, where diamond has a connection of carbon atoms in 3 dimensions. So we have all these carbon atoms connected together, and diamond, having a tremendous number of covalent bonds, allows the diamond structure to have a very strong lattice structure, has a very high melting point and boiling point as a result of having lots and lots of interconnected covalent bonds. So it's kind of like a 3-dimensional array of covalent bonds, whereas maybe something like methane would just be covalent bonds in one molecule, then we'd have another molecule with separate covalent bonds, then with intermolecular attractions together, forming overall much weaker connections than if we could somehow connect all the atoms in a sample together with covalent bonds. So covalent bonds can be strong if we have a network structure where we have the entire structure connected by covalent bonds. If we have just molecules connected by covalent bonds and then adjacent molecules connected by weak forces, the weakest being dispersion, this is the type of force we see in nonpolar molecules, and so that allows, that makes N2 boil and melt at a really low temperature. So if we imagine going like 0 Kelvin and warming a sample up, nitrogen doesn't take much kinetic energy at all to melt because it has weak attractions for itself. HCl, HF a little bit stronger because we have polar molecules. HF is more polar because it's smaller, more polar. So it has a slightly higher boiling point compared to, say, HCl. And then likewise, if we then compare to LAF, ionic, very high melting points, and then metallic and covalent network compounds also have high melting points. So if we look at the types of intermolecular forces between molecules, so this is looking at molecular compounds. So for molecular compounds, where we're looking at the attraction between molecules, we can describe the attractions to either be resulting from dispersion forces. Sometimes these are called London dispersion forces, or induced dipole interactions. This is the force that will unite molecules like neon. So if neon is going to form a liquid and exists as a liquid, it has to somehow induce a small dipole in itself. So it can somehow induce a dipole moment in the molecule when there truly isn't a dipole in a average atom of neon. So neon would distribute most of its electrons symmetrically around itself. So it would have all these electrons in different types of orbitals, and that the electrons on one side of the molecule would be, as probably located as the electrons on the opposite side. But if 2 atoms can induce a dipole moment in each other, so they induce a small dipole moment, then that could give a small electrostatic attraction for neon to be attracted together. And so the dispersion force is the main type of force. We'll see this kind of demonstrated on a few more slides. But this is the basic force. It's the only force present in nonpolar compounds. Now, we also have dipole-dipole forces, so polar compounds can have dipole-dipole forces, and then polar compounds that have hydrogens attached specifically to an NO or an F, and we'll see this defined more precisely on a slide later, but hydrogen bonding results when an H bonds directly to NO or F to create an especially polar type of connection, so we get relatively high partial positive and negative charges on the atoms in these compounds, and also these atoms are particularly small. So if you recall, lattice energies are strongest on the smallest of ions. Our ionic bonds are stronger when the ions are smaller. Likewise, our polar interactions are the most strong when they are on the smallest of possible ions and of the highest possible charges. So we'll see those occur when H directly bonds to N, O, or F in some different type of compounds. The first two we sometimes call van der Waals forces. They're, and this connects back to chapter 10. So when we're looking at the van der Waals equation, that the values that have the largest A value, those are the ones that have the largest intermolecular forces. And the largest A values come from having the greatest dispersion or dipole-dipole forces. So van der Waals forces are sometimes referred to as the dispersion forces and dipole-dipole forces. So a dispersion force is any way for a nonpolar particle to become attracted to itself by inducing a dipole moment. So you think of a subatomic view, you have atom A, atom B, electrons are just randomly distributed around the atom. But if they could somehow polarize their electrons to adopt a small polarity, then you get this partial plus, partial minus attraction that can be then built in to the molecules. So atoms that more easily do this are said to be more polarizable. And so if you want to push electrons around, having more electrons would likely make that easier. And having the electrons more spread out would probably make it easier as well. So we'll see that the atoms that are smaller with fewer electrons are harder to polarize, and atoms or molecules that are longer and larger are easier to polarize, easier to push their electrons around. So some factors that account for the dispersion force and hence the boiling point. So if you compare pentane, where all your carbons are connected in a straight chain, versus neopentane, which it has the same formula, but the carbons are more connected into a ball. So this is where we have a central carbon, and then you have a CH3 group coming off in each of the positions. So here we have a CH3 group emerging from a central carbon for the same overall formula as having a linear chain of CH3, CH2, 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 CH3. So each of these have 5 total carbons, the same number of hydrogens, but having the atoms connected in a chain will allow 2 adjacent molecules to more easily push their electrons around to create a partial negative side and a partial positive side. So a linear chain molecule will be more easily polarized. That will make the molecule more attracted together. The boiling point here, 309 Kelvin, is higher than the boiling point of neopentane. So there's not as much connection between the electrons and the atoms. It's going to be harder for one molecule to push the electrons and the other molecule away to induce this dipole moment. So we're going to have a smaller negative charge emerge on these atoms, less attraction resulting. Maybe you can think of it as less contact. So you have less contact between two atoms that can interact with each other. You have more room for interaction in the longer chain molecules. So the number of electrons in an atom, more electrons, more dispersion force. The size of the atom or the shape of the molecule can play a role. If we were to compare like pentane with hexane, so you add a carbon, the boiling point's going to go up. So if you compare C5H12 with the same type of structure as C6H14, the boiling point of the C6H14 will be higher than the boiling point of the same type of structure, the C5H12. So the shapes of molecule then play a role. So the linear molecule has a greater boiling point than the more compact ball-shaped molecule like neopentane. So polarizability versus boiling point. So let's look at a few comparisons. So if we look from like neon to argon to krypton to xenon, so just increasing in the noble gas, we see the boiling points increasing because we're going to a larger atom with more electrons. So more electrons easier to push around. But if you then look at having something of relatively similar size, like 2 fluorine atoms has a much higher boiling point, 2 chlorine atoms goes higher, 2 bromine goes higher, 2 iodine goes higher. And so we're seeing relatively higher boiling points due to having now two nuclei to spread the electrons out. So the more nuclei you have, the more you can spread the electrons out, the higher the boiling points go as a result. So the harder something is to polarize, and the lower the boiling point. So neon would have a really low polarizability, hence low boiling point. So that means less intermolecular force. And so a smaller molecule or atom with a lower molecular weight or smaller size or more compact size with fewer electrons has a lower boiling point. And obviously the opposite is true. If you have a greater polarizability leading to a greater boiling point due to a greater intermolecular force for a bigger molecule, bigger molecular weight, bigger size. So when you go to the F2, Cl2, Br2, I2, we were talking back in chapter 7 about how the halogens decrease increase in boiling point and melting point as they grow larger. The reason why is polarizability is increasing. So they're becoming more polarizable. I2 can induce a dipole moment more strongly in itself than bromine can, which can do it more strongly than chlorine can, and which is more strong than what fluorine can do. And then we can also maybe even start to think a little bit about metallic bonding. We'll see this in slight more detail, though not great detail, in chapter 12. But when we start thinking of metals as having these nuclei and the electrons surrounding them in metals, that having relatively smaller nuclei allow for greater attraction of the electrons. So we're seeing more lattice-like behavior or stronger interaction of the electrons with the nuclei, the smaller the charges are. So the smaller the charges, the greater the attraction, hence why our melting point trends are the opposite for metals, that most metals are decreasing in melting point as they grow larger due to an increase in the size and a decrease in the net attraction of all those electrons with the now bigger nuclei. So dipole-dipole interactions are when we have molecules that are polar attracted to the opposite end of the molecule, so you get the plus on minus interaction. And so for polar compounds, the opposite ends of each other are attracting together. So we're looking at CH3CN in a solid phase. No, a solid phase, you're going to get a slight more ordering of the atoms or the molecules relative to each other. Liquids, these are going to be more in movement, moving around randomly around each other, but still experiencing intermolecular forces within the liquid. That's why it's still a liquid. And if we want to boil these substances, we have to break these intermolecular forces in order to boil a substance like CH3CN. So solid, the atoms are still moving. They're never motionless. Or if you go down to 0 Kelvin, then perhaps at that temperature, the atoms would be in a very slow motion or almost no motion at all. At room temperature, or whatever temperature CH3CN above 0 Kelvin is still a solid. The molecules are in some small motion, but relatively in close proximity to other atoms, not moving around the bulk part of the solid. So one atom may be wiggling a little bit back and forth, but it's not like when atoms moving to, or when molecules moving to a different part of the molecule. Liquids, of course, all the molecules are always in tumbling motion relative to each other, but still experiencing intermolecular forces. So if we look at our dipole-dipole interactions, let's start with propane, something that has relatively a dipole moment close to 0 compared to a similar size molecule. So the molecular weight's similar for dimethyl ether, but now the molecule's polar, has a dipole moment. So we have an oxygen. This is an oxygen with a CH3 group on either side of it, electron pairs. So polar, but not the most polar of molecules. So the boiling point's a little bit higher than it was for propane. Acetaldehyde, if we put a CH3 group, a carbon with a double bond, it turns out that this molecule has a greater dipole moment. If I were to give you these two molecules, I don't know if you would predict that the acetaldehyde has a bigger dipole moment, but given that it does, you would predict that that should increase its boiling point, and it does. So the boiling point of acetaldehyde is higher than the boiling point of dimethyl ether. Acetonitrile, again, I don't know if you would predict that its dipole moment would be greater. You have a nitrogen atom, but it is triple bonded, but you have this structure here, cation in the background, but you have a even greater dipole moment. Again, I don't know if you would predict that, but given that you know, or that it's a provided piece of information, the dipole moment is greater for acetonitrile, it has an even higher boiling point. So boiling point increases with increasing polarity when we're comparing molecules of similar size. Now, if we compare polar molecules that grow larger, it gets a little bit complicated because dispersion forces increase, so usually a larger molecule, even if it's a little bit less polar, could have a higher boiling point. So when molecules aren't exactly the same or very similar in size, it's a little bit hard to compare boiling point trends. And like I said, even with molecules here, it's kind of hard to predict which one is necessarily more polar. But polar is going to be higher boiling than similar size that's nonpolar. So which has a greater effect, dipole-dipole interactions or dispersion forces? Well, this is a very interesting question, because if you look at something like a hydrocarbon, you would say, well, hydrocarbons only have dispersion forces because they're nonpolar. Well, if you get up to, butane is a liquid just beyond, just about room temperature. Pentane's a liquid at room temperature. Octane boils above water's boiling point. So you can have a lot of dispersion forces between molecules as long as the molecule is relatively large. And then obviously a dipole-dipole force of attraction doesn't always make something all that attracted to itself. You look at something like H2S is polar, but it's still a gas at room temperature. So what's the difference here? How do you know how to predict how strong the intermolecular forces are? Well, I think it's comparing relative size. If you have two similar sized molecules and shaped molecules, one's polar, one's nonpolar, then the polar one's going to have the greater boiling point and the stronger attraction, hence the higher boiling point as a result. So if two molecules are comparable size and shape, dipole-dipole forces will be the dominating force. If one molecule is much larger than another, then dispersion forces will kick in. So there will be a ton of molecules that we can't necessarily compare boiling point trends easily due to the size difference not being big enough, or the polarity difference between two compounds being so similar, you don't necessarily know which one's more polar or less polar. But I think just the idea here, similar size, one's polar, the other one's not. The polar compound has a higher boiling point, and size can trump and certainly factor in an increase at boiling point. This is why we see I2 nonpolar be a solid at room temperature, is because it has a very strong dispersion force because it's a pretty heavy molecule. Okay, let's take a look at this graph here. This graph is comparing things like CH4 to then the next bigger atom from carbon is silicon down its group, then germanium, then tin. So notice that the boiling point is increasing as we go to a larger atom. Now that makes a lot of sense for CH4 to SiH4 to germanium H4 to tin H4, because these are all nonpolar. So these are all nonpolar because the molecules are all tetrahedral, so they are certainly nonpolar. Then if you look at something like NH3 to PH3, the difference between N and P is that the nitrogen is really electronegative, the molecule's polar. So NH3 is polar, and then the phosphorus is polar as well, but it's not as polar. And then the next atom down from phosphorus, I believe is arsenic, but it grows in size, and so then size kicks in, and then arsenic has a greater boiling point, as does the next one in that trend. So NH3 high, PH3 lower in terms of its boiling point. HF to HCl drops and then increases to HCl and then increases to HBr. It looks like they have these two backwards, so that should be antimony H3 instead of HI. So it looks like they have two of the names backwards in the chart. And so likewise, water high in terms of its boiling point, then drops to H2S. Room temperature is right about here. So HF has a boiling point right about room temperature. NH3, even though it's polar, even though we're going to call it a special type of polar compound that has what we call a hydrogen bond, it still has a boiling point below room temperature. Water is the only one on this chart that has a really high boiling point compared to the others. And so then you can see H2S drops to below room temperature, and then you rebound from there to selenium, and you rebound a little more up to tellurium. So this part of our trend here is dispersion forces. So we're seeing this increase here due to the increase of the size of those molecules and the increased dispersion force that results in the molecules having a greater dispersive force of attraction. And so then what about these ones here? These molecules here have an especially strong dipole-dipole force that we'll call it a hydrogen bond. So a hydrogen bond is a specific type of intermolecular force that unites molecules that have hydrogen, the smallest possible atom in a molecule, attached to the most electronegative atoms like oxygen, fluorine, car driving by, and nitrogen. Okay, so you get the most of the polar possible compounds with the smallest of possible atoms in them, giving those molecules an especially high boiling point, such that if you lose that type of bond or that type of interaction, then you have a drop in boiling point to H2S, HCl, and PH3. So we get a especially strong force of attraction in molecules like water, HF, and NH3 that's just not present in any other type of molecules seen on that chart. So the hydrogen bond is the dipole-dipole force of attraction experienced when H is directly bonded to N, O, or F. Okay, and we term these hydrogen bonds. So we get this especially strong negative and positive charge. So what's going on here is in this type of molecule, the oxygen charge is relatively high. So it's relatively high partial charge, like the magnitude of the charge is really high. And the same thing with the hydrogen charge. Also, oxygen is relatively small, hydrogen is relatively small. So you get the strongest possible charges, the highest possible charges on the smallest possible ions in these molecular compounds. That gives them a uniquely strong type of dipole-dipole force of attraction termed a hydrogen bond. So it's likewise similar in terms of HF, and the same thing with NH. Now, like I said, it doesn't make HF or NH3 particularly higher boiling than, say, relative to room temperature, but it does make them much higher boiling than you would expect if you were to compare them to HBr or HCl in the case of HF, or in the case of pH3 in the case of NH3. And so the hydrogen bond is especially strong due to the small size of the ions and the relatively high partial positive and negative charges. And you would also get hydrogen bonds between any type of molecule where you have a hydrogen directly bonded to an NO or an F with another molecule with an H directly bonded to an NO or an F. So you can have a hydrogen bond between water and ammonia molecules. You could also have a hydrogen bond between water and HF molecules as well. Just any case where you have hydrogen directly bonded to an NO or an F. So a molecule like CH3Cl or CH3F, you may look at this compound here and say, can this compound form a hydrogen bond? Well, its Lewis structure would have 3 hydrogens bonded to a carbon, fluorine bonded to a carbon. This molecule is polar, but it is not a compound that we would say has a hydrogen bond. So this compound here has no H bonds. So a hydrogen bond is a specific type of interaction when H is directly bonded to NO or F. So no H directly bonded to the F, that molecule does not have hydrogen bonding. Now, if we did want to say it had a hydrogen bond, we would probably then expect it would have a relatively high boiling point, and this compound actually doesn't have that high of a boiling point. So there's no especially strong force of attraction between adjacent molecules of CH3F. They're any more remarkable for any other similarly sized polar molecule. So this molecule here would have dispersion forces of attraction. It would have dipole-dipole forces, but it would not have H bonds. So we look at molecules of water, HF, NH3. Those molecules still have a dispersive force of attraction, and they still have a dipole-dipole force, and they have the H bond. So what forms hydrogen bonds? We get hydrogen bonding arising in parts of the molecule where we have the most electronegative atoms. So the 3 most electronegative atoms are N, O, and F. Chlorine is as electronegative as chlorine. Chlorine is as electronegative as nitrogen is, but chlorine's much bigger. So this bigger size of chlorine doesn't make the HCl bond particularly strong. It also didn't make the HCl molecule particularly high boiling. Remember, HCl boiled less than HBr. If HCl had this type of hydrogen bonding interaction, it probably would have had a higher boiling point than HBr. So there's really nothing remarkable about HCl's boiling point, but there is something remarkable about HF's boiling point. And so we get this especially strong dipole moment, creating the greatest possible charges on the smallest possible ions. Chlorine's not a small ion, so that's why it doesn't have the hydrogen bond when an H directly bonds to a chlorine. So let's compare ice to liquid water. So hydrogen bonding makes the molecules farther apart in ice than in liquid water. So when ice forms its crystal, it forms a regular repeating pattern. It actually makes the crystal grow larger in size. And growing larger in size has the effect of having then the same mass with a larger size to decrease the density. So when you freeze liquid water, it expands, and if you put things like water bottles in the freezer that aren't strong enough to hold the bottle in, then the bottle shatters. And so that's because of the density of ice resulting from the hydrogen bonds pushing the molecules apart in ice compared to liquid water. So molecules in liquid water get closer together due to hydrogen bonding. So Ion-Dipole forces can be understood as well. So this is the reason why something like sodium chloride dissolves in water. We talked about this back in chapter 4, was that the water molecule H atoms all have a small positive charge that can surround the chlorine minus ion. You just get a lot of water molecules that do this. You get a very strong ion-dipole force of attraction, the opposite for sodium plus being surrounded by the oxygen group with its partial negative charge. So you get a shell of water surrounding each of the ions, the hydrogens towards the minus, the oxygens towards the plus ions. And these ion-dipole forces collectively must have been stronger than the ion interactions in NaCl because they're replacing those strong lattice forces between Na plus and Cl minus. So the ion-dipole forces in compounds that dissolve in water end up being stronger in net and in total compared to the lattice energy of that solid compound to begin with. So the strength of these forces is what makes these ionic substances able to dissolve in polar solvents like water. So if you take an ionic compound that dissolves in something like water, usually it doesn't dissolve in something like, pick any nonpolar solvent that you wish. So like CCl4 is a nonpolar molecule that's a solvent. You're not going to get something like NaCl to dissolve in CCl4 because CCl4 doesn't have charges that can stabilize or surround the ions and create a very strong ion-dipole force of attraction. So let's compare the dispersion force, dipole-dipole force, H bonding, and ion-dipole forces. And so the dispersion forces are generally the weakest, but again, they can grow large if the molecules are large. Dipole-dipole forces are kind of intermediate. They can be strong as stronger when the molecules are more polar. And then if the molecules are really small with the H bonded directly to an NO or an F, then you can have a really strong dipole-dipole force that we call the H bond. And then ion-dipole forces are even stronger because we have a full plus interacting with a polar solvent. And so atoms, like noble gases, they experience dispersion forces only. If we look at a nonpolar molecule like BF3, CH4, any type of nonpolar molecule, it also only has dispersive type forces, or that induced dipole interaction. If you look at a polar molecule without OH bonds or NH bonds or HF bonds on the molecule, so like HCl, CH3CN, CH3F, any case where you do not have H directly attached to NO or an F, you still have dispersion forces of attraction, and then you would still have a dipole-dipole force of attraction. So in other words, the molecules have a dipole moment that could attract two molecules together, and then the molecule can even induce a slightly bigger dipole moment through the induced dipole interaction. So all chemicals exhibit the dispersion forces of attraction. The strongest force dictates the extent of the attractions in the molecule. So most of the time you'll look at the strongest force to kind of determine the property of a substance. Like a polar molecule should have a relatively higher dipole moment compared to a similar size molecule with just dispersion forces. And so then let's look at a polar molecule that has OH, NH, or FH groups on the molecule, like water, NH3, HF, methanol, ethanol. Those types of molecules have dispersion forces, dipole-dipole forces, and H bonds. And the hydrogen bonding would lead you to believe that these compounds would have the greatest possible boiling points compared to similar size molecules without H bonds. And so then, but you can still have dispersion forces like methanol, ethanol, propanol increase in boiling point because you're growing the size of the molecule and keeping the polarity relatively similar. You still have the H bond present as well. Okay, so then we look at an ionic substance dissolved in water, so NaCl in water, or any compound you know to be soluble in water, you get all of these interactions. So you get the dispersion forces, you get the dipole-dipole forces, you get the H bonding forces, and you get the dipole forces of the solvent molecules surrounding the charged ions. Go over a couple generalizations here about relative strengths of intermolecular forces. So we're looking at acetic acid. So acetic acid has a molar mass of 60 atomic mass units, boiling point of 390. We can compare that with 1 propanol, which has the same molecular weight but a lower boiling point. So when we're comparing these compounds, we can see, well, they have the same size, so they should have the same overall dispersive force. They would have to have different dipole moments to differ in dispersion forces as well, or different in shape by a fair bit, and these molecules are pretty similar in their overall shape. What makes these molecules different is the one must have a stronger H bond. We actually get 2 types of H bonds out of the acetic acid molecule, but only 1 H bond out of the 1 propanol. So if we can somehow account for the number of H bonds, the more H bonds we can get between adjacent molecules, the stronger the attractive force will be between those molecules. So 1 H bond, relatively low boiling point, 2 H bonds, relatively higher boiling point. So what we want to do when we're comparing molecules is that they're both nonpolar, compare their shapes. The longer molecule or the more elongated one will have the greater boiling point due to the greater intermolecular force. If one of the molecules is polar and the other is nonpolar, then the polar is higher. If one can H bond, then it has a stronger or higher boiling point due to greater forces than something without H bonds. And then if both molecules can H bond, you might inspect the structure to see if one of the molecules can adopt more types of H bonds than one of the other structures. So one of the keys here is not always predicting boiling point trends, but maybe explaining or trying to understand boiling point trends. Because like I said, you can't always predict which compound's more or less polar than another. Sometimes it's hard to look at a molecule and try to count up how many H bonds it can form, but once you see a structure, you can then maybe understand and relate a trend once you kind of see two structures lined up with each other and can start counting H bonds. So there are some liquid properties that are affected by intermolecular forces, so things like boiling point, as we've been discussing all along. Melting point follows along with the same analogy, that the stronger, or that maybe we haven't talked about this too much for melting, but when we look at molecular compounds in the solid phase, so like ice, anything that's frozen in its solid structure, that you still have an intact molecule that's interacting with the other molecules through intermolecular forces, and so the stronger the forces, then the higher the melting point will be. Now we'll look at viscosity as well. Viscosity has to do with the resistance that a liquid has to flow. So the stronger the attraction between the stronger the attraction is between adjacent molecules, the greater that resistance to flow will be. Surface tension is the energy you have to input on a surface to break the surface. You'll have to put a greater amount of energy on a surface the stronger the attractions are with those molecules. And so then capillary action is the, if you're looking at the rise of a meniscus on a glass type cylinder with water filling the cylinder, then you're going to get a greater surface attraction between the water and the molecules and the glass. You'll get a greater capillary action with the stronger the forces between the liquid and that solid structure. So the greater the attraction here between these molecules, then the greater the capillary action. So viscosity is the resistance of a liquid to flow. It is related to the ease with which molecules move past each other. Viscosity increases with stronger intermolecular forces and decreases with temperature. So at a higher temperature, as temperature increases, then the molecules have energy to overcome their attractions with each other. You don't really weaken the intermolecular forces of attraction with temperature. What you do is you give the molecules more kinetic energy so they have enough energy to break those attractive forces. Just like as you increase the temperature, you give the molecules more energy to break their attractive forces and eventually boil. You also then weaken the intermolecular, you don't weaken the forces. You lessen the nature of the molecules to be attracted together so that they more easily flow around each other and have hence a lower viscosity. So the greater the resistance to flow, the greater the viscosity. We can reduce that viscosity by increasing the temperature. We can strengthen the viscosity with a longer chain hydrocarbon. So most of our oils are made up of hydrocarbons. So if you have like a C3, CH2, say 10 CH3 has one viscosity, compare that with CH3, CH2, 20 CH3, the viscosity here will be much higher due to the longer chain. So if you lengthen the chain of your hydrocarbon, you'll more have a thicker, harder to flow liquid as a result. So this slide here is comparing some relatively smaller hydrocarbons for hexane, heptane, octane, nonane, and decane, seeing that their viscosities very regularly are increasing. So heptane's a little bit higher than hexane, octane's higher, going up. 7.1 times 10 to the minus 4 is bigger than 5.42 times 10 to the minus 4, and then even bigger for decane. So if you want a really viscous hydrocarbon, then you want a very long chain hydrocarbon. And if you think of a branched hydrocarbon, like if you ball the structure up and have a more compact hydrocarbon, you're going to have that serve to reduce the attractive nature of the molecules with each other, and you're going to reduce the viscosity as a result if you have a more branched type structure. So water has a relatively strong force of attraction, so that causes adjacent water molecules to be pretty well attracted to each other, and it takes a fair bit to break the surface of water. This is one of the main reasons why insects can float or sit on water. It's due to the surface tension of water. So when the insect has its leg on the water molecules are kind of beating together, forming a big droplet that is harder to break as a result. So cohesion and adhesion can be understood. Cohesive forces are the intermolecular forces that bind similar molecules to one another, and adhesive forces are the forces that bind a substance to a surface. So cohesion, molecules together. in adhesion, molecules to a surface. Okay, so you can think of the relative cohesion and adhesion, if you think of a liquid in terms of how it's attracted to itself with how it's attracted to this actual solid surface of the container it's in. So this is why most liquids have a positive meniscus, and it has a positive meniscus because most molecules are more attracted to the solid, so they have a stronger adhesion with the container they're in compared to the cohesive forces they have with the molecules that they're surrounded by in the liquid phase. And so these are the important forces in capillary action. So if the molecules have a stronger attraction with your plant materials in the stem of a plant, then the water molecules can travel up the stem because they're more attracted to the stem than they are to each other. They have a stronger adhesive force with the stem than their cohesive forces with each other. So capillary action can be seen in things like water. Water has a strong affinity with glass because glass has a lot of silicates in the surface, and silicates have lots of polar type structures on them. So silicates have lots of SiO2 units, and SiO2 would be a polar type group in glass. You get this polar like-on-like interaction. Something that maybe doesn't come up in terms of a term until chapter 13 is this like dissolves like idea, that substances of similar types of intermolecular forces tend to interact with each other. So molecules that are polar interact with other polar molecules very easily. And likewise, the opposite sometimes turns out to be the case, that a metal doesn't have a strong affinity with something that's polar. So unlike forces tend to repel each other. So metals tend to repel polar forces of attraction. So the metal atoms actually have a stronger cohesive set of interactions than they do with the adhesive interactions with glass. So you see a downward meniscus. So for the case of mercury, you get a downward meniscus because the cohesive forces are stronger than the adhesive forces, and then you get the upward meniscus for water because the adhesive forces are greater than the cohesive forces. The attraction with the water molecules with the glass are stronger than the water molecules with each other. Okay, so I was considering doing a full video for all of Chapter 11 together. This video has probably gone long enough, so I'm going to go ahead and stop here. So this is all for the first half of the video for Chapter 11. Thanks for the attention. See you in class.